Hey everyone, so this is the solution video to worksheet 10.6. We're going to be talking about inverse trig functions in this one. So we're going to start off with number one, finding the arcsine of -1. Now, we know that the arcsine has a restricted range as well as a restricted domain. And in terms of what we can expect to get out of the arcsine, we know it's going to be an angle. And in the case of the arcsine, we know that we're going to get some angle that will be on the interval from -π/2 to +π/2. So we're going to be looking for some angle that's either in the fourth or the first quadrant. So we know that this interval consists of quadrant 4 and quadrant 1. Now the tricky thing about this is that normally, especially if we're used to using the unit circle, we think of the fourth quadrant as the tail end of the interval from 0 to 2π. But in this case we have to think of that fourth quadrant as from 0 to -π/2 in terms of a negative angle of rotation. We'll see that a little bit more clear in a second. So here's what I might recommend you sort of ask yourself when you get a problem like this. So if we're asked to find the exact value of the arcsine of -1, we'll sort of use the inverse relationship of the arcsine and the sine and consider this. Let's ask ourselves, when is the sine function equal to -1 on this restricted interval that we have here? So that's what we're really going to ask ourselves here. So let's sketch this out. I think a sketch really kind of helps drive this idea home. So we're gonna sketch the two quadrants that we're going to consider here. So we've got quadrant 1 and then we've got quadrant 4. And again, the angles that we're going to be looking at are just the angles from 0 to π/2 and then from 0 to -π/2. So it's these angles and these angles. Okay, so when is the sine equal to -1? Well, it's going to be equal to either positive or -1 on the y-axis. Specifically, we're going to see that our solution angle is going to be on the negative side of the y-axis. We know that if we were to rotate to the negative side of the y-axis, that the sine of -π/2 is going to be equal to -1. That's in here, right within the fourth quadrant. So resist the urge to call this 3π/2 because 3π/2 does not fall into this restricted range for the arcsine. So we need to think of this angle of rotation as -90 degrees or -π/2. So here's what we can consider now. So since the sine of -π/2 is equal to -1, and since -π/2 is on our restricted interval of angles that we can expect to get out of the arcsine, then we can conclude that the arcsine of -1 is equal to that angle, -π/2. So that would be our solution for part A. And we kind of go through the same process for all of these, as we'll see. All right, so for part B, we want to find the inverse sine, or the arcsine, it's a different type of notation, of the square root of 3 divided by 2. So again, let's ask ourselves a question here. Let's consider that this is asking us to figure out when is the sine function. So when is the sine equal to the square root of 3/2 on that restricted interval? So on the interval from -π/2 to +π/2. So we ask ourselves this question, and then let's go ahead and sketch out these two quadrants that we're going to be looking at. Okay, so we've got our angles up to π/2 and then down to -π/2. Well, we know that this is going to occur in the first quadrant because the sine is positive in the first quadrant as opposed to the fourth. And then we think, well, what about the reference angle? You know, when is the sine going to take that value of root 3 over 2? Well, that's going to happen up here at that 60 degree, or that pi over 3 reference angle. So we know if we were to look at that 60 degree reference triangle in the first quadrant, so we got our 2, we got our root 3, we've got our 1. The sine of this angle here is the square root of 3 over 2. So that's what we're going to be looking for. So we go ahead and we say that, so since the sine of 60 degrees, or in this case pi over 3, should be that first quadrant angle, is equal to the square root of 3 divided by 2, again opposite, divided by hypotenuse, root 3 over 2, and, because we have to consider this also, since pi over 3 is an angle on the interval from minus pi over 2 to positive pi over 2, then we can conclude that the inverse sine of root 3 divided by 2 is equal to pi over 3. So again, really think about this, what these two statements are saying. You know, we're reversing the role. Here at the sine, we plug in the angle, we get out the ratio of sides. For the arc sine, we put in the ratio of sides, and we get back the angle, which we associate with that. Okay, so that'll take it for B. Part C, we're going to look at the arc cosine now. Now with the arc cosine, we know that we're going to be looking at a different set of restricted angles here. We know that the arc cosine spits out angles between 0 and pi. So what we should expect to get out of here is some angle on the interval from 0 to pi. So when we try to visualize this, we'll be looking, in this case, for angles in quadrant 1 and in quadrant 2. Okay, and if we ask ourselves the same question we had before, just think of it in terms of cosine, the arc cosine of -1 sort of prompts us to ask, well, when is the cosine equal to -1? Again, on the interval from 0 to pi. Well, let's see. We can go ahead and we can draw our two quadrants. So here we're going to get quadrants 1 and 2. So this is our rotation from 0 to pi. So we can look at all of these angles right here in these two quadrants for the cosine. Okay, so -1. So the cosine is either positive or -1 on the x-axis. It's -1 on the negative x-axis. So our actual solution angle here is this full angle of rotation from 0 to pi. So that would be our full angle. So since the cosine of pi is equal to -1, and since pi is an angle that we have available to us on this interval, so is on the interval from 0 to pi, barely, then we can say that the arc cosine of -1 is equal to pi. And that would be our solution for that one. So same type of process, we just maybe have to consider a different range of angles with the arc cosine. Okay, so the arc tangent. Now the arc tangent we define as the inverse of the tangent function, and it also has a restricted range of angles that we can expect to get out of it. Specifically, the arc tangent is going to give some angle on the interval from -pi/2 to +pi/2. And we can't include those two angles because the tangent is undefined there. But that'll be the interval of angles we'll be looking for. So we'll go ahead and we'll ask ourselves the similar question we've done for the first three. We'll say, well, when is the tangent equal to the square root of 3 on the interval from minus pi over 2 to pi over 2. So if we sketch sort of the first and the fourth quadrants like we did with the arc sine. So here's pi over 2, which we can't use, and minus pi over 2, which we can't use. Well, think about this. Well, the tangent is positive in terms of these two quadrants. It's going to be positive in the first quadrant. So we can at least look there. And then we just need to determine, well, what's our reference angle going to be here? Well, if we were to rotate 60 degrees, or pi over 3, and we drew our reference triangle there for the 30, 60, 90 right triangle, we've got this side is 2, square root of 3, 1. We know that the tangent is the ratio between the opposite and the adjacent side, which gives us the square root of 3, which is what we're looking for. So we know that since the tangent of pi over 3 is equal to the square root of 3, and since pi over 3 is on the interval from minus pi over 2 to pi over 2, then we can say that the arctan of root 3 is equal to pi over 3. So hopefully you're kind of seeing how this process works, and the only thing we really have to be mindful of are our restricted range of angles for the specific inverse trig function, and then being able to locate these angles using the skills that we developed in solving trig equations in 10.2 and evaluating trig functions for that matter. All right, so let's do another one with the arctan. So we've got the arctan of negative root 3 now. So we know the interval that we'll be looking for on the angles like it was in D, except here what we'll ask ourselves is, when is the tangent equal to negative root 3 on our interval from minus pi over 2 to positive pi over 2. Let's see. So we'll draw our two quadrants that we'll be looking in. So from pi over 2 to minus pi over 2. And the tangent is negative in the fourth quadrant. So we'll go down here, and we're going to use the same reference triangle, except we're going to rotate negatively. So if we rotated negative 60 degrees, or negative pi over 3, we'd get the reference triangle where we've got 2, 1, and negative root 3 as our opposite. So again, the tangent of the angle is going to be the opposite side divided by the adjacent side, so we get what we're looking for. So since the tangent of negative pi over 3 is equal to negative square root of 3, and since negative pi over 3 is on the interval from negative pi over 2 to positive pi over 2, the range of the arctangent, then we can say that the arctan of minus root 3 is equal to negative pi over 3. And again, the common mistake you'd want to avoid here is saying that this was 5 pi over 3. You know, especially if you use a unit circle, you're probably used to seeing this angle of rotation in a positive direction and saying, well, this is 5 pi over 3. Well, that's not right, because that angle is not in the restricted range of the arctan. Okay, last one, arcsecant of 2. So the arcsecant, we've got a restricted set of angles that we can get out of this that is defined as this. So the angles coming out of the arcsecant will be some angle in general on the interval from 0 to pi over 2, unioned with pi over 2 to pi. Now notice this is almost the exact same set of angles that we get out of the arc cosine, which is the reciprocal function of the arcsecant, except we're leaving out pi over 2 because the secant is undefined at pi over 2. So we don't include that as a possible angle or an output of the arcsecant. So we got two ways of thinking about this, really. So one way that we could consider this is we just think of it straight up as an arcsecant problem. And we could say, well, when is the secant function equal to 2 on this restricted interval of angles that we have? That's when we could do it. If you're comfortable with the secant function, that's probably a pretty easy question to answer. If we're a little unsure with the secant and we want to think about it as either sine, cosine, or tangent, we know that the arcsecant of 2 will actually be equal to the arc cosine of its reciprocal 1/2. And this might be a little bit easier for us to stomach. So we could ask ourselves from this, well, when is the cosine equal to 1/2 on, again, this restricted set of angles that we have here? So you could really think of this in either way, using the fact that reciprocal functions of each other, or just going straight to the secant. Let's go ahead and sketch it either way. We need to consider the two quadrants that we'll be looking at. So we've got our quadrants, and we're going from 0 to pi. We will not be including pi over 2 as a possibility, so we'll just leave that one angle out. So however we want to think about it, we know that it's going to be positive. So we're going to be in the first quadrant, because the cosine is positive in the first quadrant and the secant is positive in the first quadrant. So whether we're thinking about this or we're thinking about this, we know we're going to be in quadrant 1. And if we were to draw a reference triangle using a 60-degree or pi over 3 reference angle and set this up, we've got 2, 1, square root of 3. So again, however you want to think about it, cosine is the ratio between the adjacent side and the hypotenuse. There's our 1/2. Or the secant is the ratio between the hypotenuse and the adjacent side, which would still give us 2. So it's the answer to either of these. So we see in both cases that in one, the secant of pi over 3 is equal to 2 divided by 1, or 2, check. And if we had gone the route of option 2, we would see that the cosine of pi over 3 is equal to 1 over 2, which is what we wanted, 1/2. So regardless, we conclude that the arcsecant of 2 is going to be equal to pi over 3. So pi over 3 has been a busy angle for this worksheet. Okay, so that's how you would do these for any type of, just evaluate the arc trig function or the inverse trig function, is to keep in mind the restricted set of angles and then sketch it out. Okay, so for number 2, it says find the exact value of the sine of the inverse cosine of 1/2. Well, let's address this first. And we actually answered this question in the last problem that we did. We wanted to find out, well, what is the arc cosine or the inverse cosine of 1/2? Meaning, for what angle does the cosine equal 1/2? Well, we know from problem number 1 that this is going to end up being pi over 3. So this is like number 1. That's how we would figure that out. So now we're going to go ahead and we're going to take that output. So this term in here, the inverse cosine of 1/2, is actually equal to 1/3. So we're going to take that and we're just going to put it back into our function. So this now gives us the following. So we've got the sine of pi over 3. Well, this is just a simple evaluate the trig function. We know this from 10.2 that the sine of pi over 3 is the square root of 3 divided by 2. And that'll be our solution. Okay, so we're just using the skills we got from problem number 1 to help us simplify and evaluate a problem like this. Okay, lastly, number 3. So we're going to take this kind of unpleasant trigonometric expression, the sine of the arc cosine of x, and we're going to rewrite this as an algebraic expression of x. So we're going to totally ditch the trig functions and just have an algebraic expression. Now this is how we're going to do this, is we're going to consider that even though we don't have a specific value to plug in for x, we know that the arc cosine of x, that's going to be some angle. We know that quantity in there is an angle. So what we're going to do is we're going to let the arc cosine of x just be equal to theta. So we're just going to kind of sub that out. We're going to let that equal a random angle theta. So if we were to go ahead and take this and take the cosine of both sides here, so we're going to take the cosine of the arc cosine of x, and then we're going to take the cosine of theta. Well, taking the cosine of the arc cosine is composing a function with its inverse, which will they'll undo each other. And what we'll be left with is that the cosine of theta will just be equal to x. So once we've got this, so we do our substitution first, the next thing we're going to do is we're going to draw a triangle for theta. So draw a triangle for theta. And this is really the fundamental step of this problem, is being able to do this. So I'm going to draw this off to the side here. So we're going to just draw a nice little random right triangle. And we're going to put theta down here. It doesn't matter where we put it as long as it's not the right angle. Now we know already from this substitution right here that the cosine of theta is equal to x. Well, the cosine of theta we define as the adjacent side divided by the hypotenuse. And if we know that this is equal to x, well, let's think of this as just x over 1. So that means that our adjacent side is x and our hypotenuse is 1. So let's start to fill that out on our triangle over here. So there's our hypotenuse 1. Here's our side adjacent to theta, which is x. Now all we need to do is figure out the opposite side. So next is we need the opposite side to fill out this triangle. We know that the opposite side can be found because the opposite side squared plus the adjacent side squared is equal to the hypotenuse squared by the Pythagorean theorem. So this tells us that the opposite side squared is going to be equal to 1 minus x squared, or that our opposite side will be equal to the square root of 1 minus x squared. So now we can go ahead and we can fill that in up here, and we've got the square root of 1 minus x squared. So now that we've got this triangle, we're going to go back to the original problem. So back to the original problem. And what we see here is that originally we were asked to find the sine of the arc cosine of x. Well, we decided to let the arc cosine be equal to theta. So now we've got the sine of this angle theta. And we know that the sine of theta for any right triangle is the ratio between the opposite side and the hypotenuse, which we now have a triangle for. And the opposite side is the square root of 1 minus x squared. The hypotenuse is 1. So we can conclude that the sine of the arc cosine of x, so this nasty composition of a trig function and an inverse trig function, is actually able to be simplified as an algebraic function of x, specifically 1 minus x squared. Good problem to know how to do for pre-calculus and then also when we move on to calculus. So there's a quick substitution. Drawing the triangle, you can see, is really the crux of this problem, and then we go back and we reevaluate the triangle to rearrange our problem as an expression of x as an algebraic function. Okay, so that does it for 10.6, and I will see you all in the next video.